Okay, in this video, I'm going to talk about basis for topology. Before we start talking about basis for topology, let me define open set in a topological space. Open set. Okay, let's say X is a topological space. Topological space with topology tau. Let's say X is a topological space with the topology tau, and U is a subset of X. Then this subset U is open set of X if U is an element of our topology tau. So this is the definition of open set in a topological space. X is a topological space with the topology tau. Then a subset U of X is an open set of X if U is an element of the topology tau. So from this definition, you can see that we know that if tau is a topology in a given set X, then this tau always contains the set X itself and the empty set. So from this definition, we can say that the given set X and the empty set, they are always open set in X, because empty set and the whole set X, they always in the topology tau in the given set. Let me give you example of the open set in the given set. Let's say example. Let's say X is a set with two elements and whose elements are, or let's say 1 and 2, and tau is a topology on X whose elements are empty set and the whole set X, and then this set whose element is 1. So it is easy to check that this collection is a topology on the set X. So you can use the definition of topology to check whether this tau is a topology on X or not. But like I said, it is easy to check this tau is a topology on X. Now, from this definition of open set, we can say that phi X and 1, these are open set in X. Okay, so these are the open set in X, and the question is, are these only the open set of X? No, it depends on the topology. Let's say in your topology you have another set, another singleton set whose element is 2, then that's gonna be also the open set in X. So which subset of the given set is open set? It depends on the topology defined on that set. Anyway, open set of the given set X is simply an element of the topology tau on the given set X. So from this definition, we can see that so in our previous video, which was about topological space, so we defined the topology using all the open set of the given set X. And so to describe the topology, using all the open set of the given set, sometimes it's going to be too difficult because you need to find all the open set of the given set to describe the topology on the given set. So instead of using all the open set of the given set to describe the topology, there is another way to describe the topology where we can use a smaller collection of the open set of X. And if you describe the topology, if you can describe the topology using the smaller collection of the open set of given X, given set X, then that smaller collection is called the basis for the topology in the given set X. Now, let me give you the formal definition of the basis for the topology on the given set X. Then I will give you some example of the basis for a topology on the given set X. Okay, so here is the formal definition of the basis for the for a topology on the given set X. Let's say X is our given set, and script B is the collection of subset is a collection of subset of X. Let's say X is a set and script B is the collection of subset of X. Then this collection of the subset of X, this collection is script B, then this script B is a basis for a topology on X if this collection script B, which is this collection of the subset of the X, is called the basis for a topology on X if it satisfies the following two property. The first one, and the elements of this collection script B, which are subset of X, those elements are called the basis element. I'm going to use the terminology basis element. Basis element means these are the element of this collection script B, and which are nothing, just the subset of X. And this collection script B is called a basis for a topology on X if it satisfies the following two properties. The first one is, for each X is in the set X, this lowercase x, which is an element of the given set X. For each X in X, there is at least one basis element. Let me call that is a B, uppercase B. For each X in X, there is at least one B in this collection, such that element X, this lowercase x, is in this basis element. So basically this property, it tells us that for every element of the given set X, there is at least one basis element which contains that element of X. And graphically you can describe this property like this. Let's say this is our set X, and this is an element of our set X. So for each element of this set X, you have a basis element B. Okay, let me write down this. You have a basis element B that contains this element of X, and this property should be true for each element of the given set X. That's the first property. If this script B, which is the collection of subset of X, if this script B satisfy this property, and the second one is if X, this is lowercase x, which is an element of the given set X, if X is in the intersection, if X is in the intersection of two basis elements means these are the elements of script B. If X is in the intersection of two basis elements B1 and B2, then there is another basis element. There is a basis element B3 that contains this element X. Then there is a basis element B3 containing X such that the B3 is inside the intersection of B1 and B2. So that's the second property. Should script B satisfy? If X is in the intersection of two basis elements, then there should be at least one basis element which contains the set X. Let's call that basis element is B3, and that basis element B3, it should be inside the intersection of those two basis elements. So graphically you can describe this property like this. Let's say I have this set X, and this X, which is an element of this set given set X, and let's call this is our first basis element B1, and this is our second basis element B2. Now you can see here the intersection of those two basis element is this part, and then this element X, which is in the intersection of those two basis element. If X is in the intersection of those two basis element, then there should be another basis element B3 which contains the element X and is inside their intersection. If the collection script B, which is the collection of the subset of X, satisfies these two property, then that collection script B is called a basis for a topology on X. Now let me give you example of a basis for a topology on the given set. Example, let's say X is a set whose elements are A and B, and let's take the collection of the subset of this set. Let's take this collection, which first element is the singleton set A, and then second element is another singleton set B. Now you can see this script B, which are these element of the script B, which are the subset of this set X. So we have the collection of the subset of X. Then this collection is a basis for a topology. Is a basis for a topology on this given set X. Topology on X, and it is easy to check. It is easy to check that this collection is a basis for a topology on X. So you can check like this. So if we use our definition for a basis, So in order to check whether this collection is a basis for a topology on X or not, so the first property, no matter which element of the no matter which element you pick from this set X, then there should be a um, uh, basis element containing that element of the set X. Now you can see here there are two elements of the set X, which one of them is A, and we have a basis element, this singleton set, which contains A, and for the other element B, so we have another singleton set B, which contains the this second element B of the set X. So our first property is true. And the second property, it tells you that if there is an element in the intersection of two basis element, then there should be another basis element which contains that element, and and that basis element is gonna be inside the intersection of those two basis element. Now in this collection we just have two basis element, which are the those two singleton, and if you take the intersection of those two singleton, that's the empty set. Since there is no we don't have any element in the intersection of those two basis element, so second property is gonna be obviously true, because we need the second property only if there is an element in the intersection of two basis element. But in our case, in our example, there are only two basis element and their intersection is empty set. That means in their intersection there is nothing. So obviously the second property is also true. So these collections satisfy both property of the basis for a topology, so that this collection is a basis for a topology on X. Now you can see in this example our set is a set with two elements A and B, and then our collection is the set of the singleton subset of the given set. So in fact, if you have given set and then the collection of the singleton subset of that set always forms a basis. Let me write down this one as a note. The collection of all one point set, which are also called the singleton, the collection of all one point sets of the given set X is a basis for a topology on X. So this note is very important. So if, this note, it tells us that if you have a given set and if you take the all the one point subset of the given set, or if you take all the singleton subset of the given set, then that collection forms a basis for a topology on the given set X. You can see the example here. Okay, now one more example. So from the definition of topology, from the definition of basis for topology, we saw that so basis for a topology is a collection of subset of the given set. But all the collection of the subset of given set may not be a basis, or it may not be a basis. Let me give you an example. Let's say X is a set A, B, C, D. So we have a set B, and let's take this collection of the subset of the set of the given set. So in our collection, and this is our first subset, and obviously you can say this is the subset of X, and another subset is B, C, and D. So we have this collection of the subset of the given set, and this collection is not a basis, is not a basis for our topology on X. Let's see why. Uh, uh, if it is basis, it should satisfy both topology. And now let's check whether it satisfies the first property for the basis or not. First property, it tells you that for each element of the set X, you should have an element in B containing that element. Now let's take A, which is an element of X. So A is in A is in the first set in our collection, so that's fine. If you take the second element B, which is in both sets, so that's also fine. Third element C, which is in the first and second set here, so that's fine. And the last one is D, which is in the second set. So this collection satisfies their first property, because no matter which element you pick from the set X, that element is gonna be one of these one of the element of this collection is script B. So the first property is true. Now let's see whether this B satisfy the second property for a basis or not. So second property, it tells you that if there is an element in the intersection of those two basis element, then there should be the basis element which contains that element, and it's gonna that basis element, it should be inside the intersection of those two basis element. Now these are our basis element here, A, B and C. And if you take the intersection of these two basis element, now you can see the intersection is B and C. Now from this intersection we can say that B is in this intersection, because the intersection of those two basis element is B and C, so B is in their intersection. So in order to satisfy the second property, what we need is we need at least one element in this collection, or we need at least one set in this collection which contains this lowercase b, or the element B, and that element should be inside inside this intersection. Now you can see B, this lowercase b is inside the first set, but this set is not in their intersection, because the intersection is simply B, C. And also B is in the second set of this collection, but this set is not in their intersection, because the intersection is simply B and C, but this set has also D. So that means this guy B is inside their intersection, but there is no element or there is no set in this collection which is inside their intersection, because there are only two possibilities. There are only two sets in script B which contain B, and both neither of them, they are inside they are inside this intersection. So this collection does not satisfy the second property. That's why this collection is not a basis. So that means all the collection of subset of the given set, it may not form a basis for the topology. Okay, now let me give you couple of more example of basis. Let's say X is R2, which is the plane. Okay, let's say this is y-axis, and let's take y-axis as R, and this is x-axis, which is, let's take x-axis is also R. So our set X is the R2, or if you want you can say a Cartesian product of R with itself. All right, now the collection, let me take the collection. Script B is the collection of all circular regions in this plane R2 or in X. So basically script B is the collection of all the circular region. So if there are like, you can draw bonds of circular region in the R2. So and this script B is the collection of those circular region. Okay, now we can check whether this collection script B forms a basis for a topology on R2 or not. So if this collection forms a basis for a topology on R2, it should satisfy both property. The first property, it tells you that no matter which point you pick on R2 or on the plane, you should able to construct a circle outside of that point, for example. And that is true. We can, let's say, if you pick a point here, now we can draw a circular region, in the plane that contains this point. And if you pick the another point here, so also you can draw the circular region which contains the point, and the circle lies on this plane. So no matter which point you pick on the plane, you can have a circle containing that point. So that means our first property is true. And for the second one, the second property, it tells us that if you have a point in the plane which is in the intersection of the two circles, let's say I have a point P, this point, and which is the intersection of two circles. Let's say this is our first circle. Let me call it B1, which is the element of script B. That basically B1 is a circular region. And then I have another circle here, which is B2. Now you can see here the intersection of these two circle is this part. So the second property, it tells you that if there is an element, let's say this guy, if there is an element in the intersection of those two circles, which is this one, then you should have, or there should be another circle inside this intersection containing this point of the intersection. And we can draw the circle inside this intersection which contains this point. Let's call this circle is B3. So that means if there is a point in the plane which is in the intersection of two circular region, then we can draw the circle inside their intersection containing that point. So that means the second property is also true. So the collection of all the circular region in R2 also forms a basis. So this is a basis for topology on R2. Okay, let me give you one more example, then we're done with the basis. A similar example to the previous one, let's say X is R2, which is the Cartesian product of R with itself, is a plane. This is R and this one is R. We are taking both X and Y axis or coordinate axis are like a real line. Let's say X is R, and then let me take the collection. Let me define this collection, which is the collection of all rectangular region or rectangular region. So the script B is the collection of all the rectangular region. Now our rectangles, these rectangles, we are taking the collection of rectangular region or rectangles. So the rectangles, let's form the rectangle in such a way that sides of those rectangles are parallel to coordinate axes. coordinate axis. Okay, so basically we are taking like this rectangle. You can see this is script B is the collection of those rectangles. You can see the sides are, those sides are parallel to y-axis, and these two sides are parallel to x-axis. We are not taking rectangle like this. I mean, this is also rectangle, but the sides are not parallel to coordinate axis. So we are taking the collection of all the rectangles in plane whose sides are parallel to coordinate axis, and this collection also forms a basis. This collection is a basis is a basis for our topology, is a basis for topology on R2, and it is easy to check. To check whether this collection is a basis for a topology on R2 or not, what you need to do is it should satisfy both property. First property, if you pick any point on the plane, then you should be able to construct or draw a rectangle containing that point now, and that is possible if you pick any point on the plane. Let me pick this point. Now I can draw the rectangle, okay, containing this point. And if you pick other points, any points, we can draw the rectangle containing that point. So the first property is true. And the second property is, let's say if there is an element which is in the intersection of two rectangle. Let's say I have this rectangle which sides are parallel to x-axis, and I have another rectangle here which sides are also parallel to x-axis. Now you can see here their intersection is this one, and the point is in their intersection. Then the second property, it tells you that then you should have another rectangle containing this point, and the rectangle is inside the intersection. Now if you look at the intersection itself, is another rectangle. Okay, so obviously this intersection is a rectangle, so this intersection contains this point and also is inside the rectangle, because inside the intersection, because our rectangle is the intersection itself. So this collection also forms a basis for a topology in the given set R2 or in the plane. So these are the some example of basis for a topology in the given set X. Okay. Now if you go back to the definition of topology, let me go back to the definition of topology. It says script B, so let's say X is a set and script B is the collection of subset of X. Then this collection is a basis for our topology on X. So the definition, it says this collection is a basis for a topology on X. That means if you have a basis for a topology on if you have a basis, then you can construct the topology using that basis. Okay, so this definition it tells us that if you have a basis, then you can you can construct a topology using this basis. Okay, now the next thing is we're going to discuss how to construct a topology using the basis. Okay, so in order to construct the topology using a basis, we need a lemma. I'm going to state a lemma without proof. If you are interested in proof, you can take a look in Munker's book. Now let me state that lemma, and we're going to use that lemma, or that lemma it tells us how to construct a topology using the basis. But like I said, I'm not going to prove this this lemma. If you are interested in proof, you can take a look in Munker's book in section 13, basis for our topology. And the lemma, the statement of lemma is, let's say let X be a set and script B be a topology, script B be a sorry not the topology, script B be a basis for a topology, topology on X. For a topology, let's call that the topology is tau. Let X be a set and script B be a basis for a topology tau on X. Then this topology tau, which is called the topology generated by B, this topology tau is called the topology generated by the basis B. Then the tau, the topology generated by basis B equals the collection of all unions of elements of script B. So basically this statement, it tells you that if you have a basis, then you can construct the basis you can construct the topology using that basis, and that topology is called the topology generated by the basis B. And that topology which is generated by script B is gonna be the collection of all possible union of the element of script B. So in order to construct the topology using the basis, what you need to do is you need to take all possible union of the elements of the basis. Okay, let me give you example. Let's say X is a element with X is a set with two elements, whose elements are A and B, and this collection whose elements are the singleton set of X. And if you look at the note after the definition of basis, that note, it tells us that the collection of all one point set of the given set forms a basis for a topology on X. So our set is a set of two elements A and B, and our collection is the set of those one point set. So is a basis for a topology tau on X. Okay, and it is easy to check, and which we have already mentioned. So now here we want to construct the topology generated by this script B, or generated by this basis. That topology, so we have called that topology tau. So as I said before, if you are constructing a topology using a basis, what you need to do is you need to take the possible union of the element of this basis. Okay, now that means you just take the union, all possible union of the elements of this basis. Now here you can see that this one point set is the element of this script B, or the element of the basis, or is a basis element. So if you take the union of this set with itself, so it's gonna be this one point set. And if you take the union of the second basis element with itself, that's gonna be itself. And then now here we are taking the union of each basis element with itself. Now let's take the union of these two elements. So if you take the union of these two one point sets, that's gonna be A comma B, which is our X. Okay, now and then also, so the lemma says all unions. That means we have to take all possible union of the basis element. So here we took the union of first basis element with itself, and then the union of second basis element with itself and their union. And then other possibility is also we can take the empty union. Okay, when you take the empty union, then that's gonna be empty set. So this is the topology generated by this basis. Is a topology generated is a topology generated by this basis script B. And if you want, you can check this collection forms of basis. You can see both X and phi, they are in the collection, and also it satisfies those remaining two properties of topology. Anyway, we don't need to check because we are using the lemma. So the lemma, it tells us that to construct the basis, to construct the topology using the basis, you just take the collection of all union of the elements of basis, or you take the collection of all union of basis elements. Uh, let me add one more note here. You can see this is the basis of one point set, and if you construct the base topology using the using the basis whose elements are one point set, then that topology is gonna be discrete topology. So in a given set, always you can have discrete and indiscrete topology. So that discrete topology is gonna you can generate the discrete topology uh, using the basis whose elements are one point set. So let me write down that as a note. Let's say X is a set and the tau is a discrete topology. Then tau is then tau can be generated by the basis consisting with all one point sets of X. So as we mentioned earlier, if you take the collection of all one point set of the given set, that collection forms a basis, and that basis generates a topology which is going to be a discrete topology, and you can see in this example. Okay, all right, now this is our first example of the topology generated by a given basis. Now let me give you one more example. Let's say my set X is this set whose elements are A, B, C, and D, and then basis is this collection of the subset of this set, and basis is the collection of these those subset, and one of them is this one, and the other subset is A, B, C, and then B, C, D. These are this collection, you can check this collection forms a basis for this for a topology on X. Now we're going to construct or we're going to compute the topology generated by this basis. Okay, so in order to compute the topology generated by the given basis, what you need to do is you just take you take the collection, or you take the collection of all the union of the union of the basis element. Okay, let me just write down that basis here. Our basis, it was the first element of the basis it was this one, and then the second one is A, B, C, and the third one is B, C, D. Now, so to take the to construct the topology generated by this basis, so as I said before, you take the union of the union of all the elements of of this basis, or you just take the all possible union of basis element. So just take the union of BC with itself is gonna be this set, and then you take the union of second set or second basis element with itself, and you're going to get the same result. And take the union of third element with itself, okay. And then now here we took the union of each element with itself. Now let's take the union of first and second. If you take the union of first and second, it's gonna be A, B, C, which is already here. And if you take the union of first with third one, it's gonna be B, C, D, which is already there. So let's take the union of second and third one. If you take the union of second and third one, it's gonna be A, B, C, and D, and which is X. So instead of writing this, just let me write down X, okay. And then if you take the union of all three, then that is also A, B, C, D, which is already listed here. Now and the one more possibility is take the empty union. When you take the empty union, you're gonna get the empty set. So this is our topology generated by this basis. So this is how you can compute the topology generated by given basis, okay. Now I'm gonna give you two more example of the topology generated by given basis. These topologies are quite popular example of the topology generated by the basis. Let's say X is the set of real numbers, or just the real line, and then let's say our basis is the collection of all open intervals, collection of all open intervals in R. So what do you mean by the open intervals? Open intervals is basically is the set of those intervals such that A is less than B and A and B are in R. So okay, so this is our basis. Basis is the for this set R. Basis is the collection of all the open intervals. Basically, open intervals means, let's say if this is our real line, then open interval is the set of those real numbers. You exclude the end point, okay. So A, B, and it is easy to check that this collection forms a basis. If this collection forms a basis, it should satisfy those two property. First property is, if you pick any real number, then there should be a open interval containing that real number, and that is obvious. If you pick any element, let's say my real number is X, and now I can construct the open set or open interval containing this element. So first property is obviously true. And the second one is, let's say if there is a real number in the intersection of two open interval, let's say my real number X, which is in the intersection of this open interval and then that one, let me call this open interval is CD. Now there should be another open interval containing X, and that open interval, it should be inside the intersection of those two open interval. Now you can see the intersection of those two open interval is gonna be another open interval itself, and obviously this intersection, this X is in the is inside this intersection, so obviously this open interval contains this X, and then also this open interval, since it is the intersection of those two open interval A, B and C, D, obviously intersection is gonna be inside their intersection. So this collection satisfy both properties, so this collection is a basis for a topology on topology in the real line R. Then the topology generated by this basis. So by using that lemma, we can construct the topology generated by this basis. Let's call that topology is tau, and according to that lemma, the topology is gonna be is going to be all is collection of all the open interval. So it's gonna be the topology generated by script B, let's call that topology is tau, is collection of all uh, open intervals, or you can say collection of all intervals of the form AB along with their arbitrary union. So this is the topology generated by this basis. So our topology has all the open intervals and their possible union, and this topology is called the standard topology on R, and this tau is called the standard topology. It's called the standard topology on R, and this is very famous example of topology in the field of topology, which is the standard topology on R. So the elements of the standard topology on R, these are basically the all the open intervals in R and then their arbitrary union. This is called the standard topology in R. One more example. Let's say again our set is the X is set of real number, and then now in previous example the basis element, they were like open interval. Now in this case we're going to take the basis element as a half open interval. That means let's call this script B is the collection of all half open intervals in R. So what do you mean by half open intervals? That means one side is closed and the other side is open. So our script B is the collection of all those intervals. One side, let's call the left side is closed and the right side is open. That means left side A is left endpoint is included, but the right endpoint is not. With A is less than B and A and B are in R. So basically, graphically, this collection or the element or our basis element are going to be like this. Let's say this is R, then it's like this one. Okay, so this one is included, but that one is not included. So our basis elements are these intervals. Okay, now it is easy to check that this collection forms of basis. Then the topology generated by this collection or the topology generated by this basis, let's call this topology is tau. Then the topology generated by this collection is the element of the topology generated by this basis is gonna be is the collection of all intervals of the form AB and their arbitrary unions. And this topology tau is called lower limit topology. This is the lower limit. Basically it comes the term lower limit, it comes from here, because in the basis element you can see the left limit or the lower limit is included. That's why this topology is called the lower limit topology. The standard topology and the lower limit topology on the real lines, these are like quite famous and popular example of topology generated by the basis. All right. Okay, so that's all about the basis for a topology on the given set X.